So today's class is software. We're going to do interface programming. Then one more lab week wildcard, and after that, we're going to step back for broader context, and all of the effort will move to the final projects. So this week is on interface and application programming. Rather than embedded code, this week is on, you could call it desktop code, but the desktop could run on embedded systems up to phones, to PCs, to supercomputers. But it's programs that talk to the embedded systems you've been developing. So the individual assignment is write an application that interfaces a user with an input or output device. As a group, I'm going to cover lots of tools. It's just compare tools. And a good example is Nadia in the VOG was a professional developer who does this for a living for things like newspapers and sites. And so she did a really interesting job this week where she used a range of tools to visualize sensor data. So each of these things you see is a different, beautiful way to take a sensor reading and convey it. And I'm going to cover lots of different tools to do this. But she did a great job of touring through endless options. This inset these are articles she's done professionally where she's done these sort of visualizations. But she has lots and lots of examples of really interesting ways to present visually something you measure. See the, oops. So yeah, lots of fun examples from Nadia for the week. So how do we do that? First thing you need to do is pick a language. So default for this week is something like a laptop to an embedded device, but you can run them on many different platforms. In fact, so the very first thing is hello world. Years ago in the venerable C language, they had a little program. It just prints out hello world. And so this is a site that has, it's the simplest, roughly the simplest thing you can do in a language is just say hello world. And so here's a list of 600 different languages that each can do hello world. In addition, esoteric languages is a really interesting, obscure offshoot, which is each of these is a language, but in some way, each of these is pathological. That they're not meant to be useful. They're experimentation in bizarre languages. It's amusing to browse through this. But against that background, and this picks up on something that I said in class, the C language dates back to Bell Labs. It's between low level and high level. It was developed for things like operating systems on computers. And a common confusion over and over is Arduino is C. Arduino is just C with libraries. But you can do C on the desktop. C is largely replaced by C++. C is just a program. C++ adds objects. So an object is code plus methods to work with the code bundled together that all modern languages let you do now. So in fact, Arduino is really C++, not C. C is a superset of C. And so you can do the assignment in C. C# is a Microsoft rewriting of the capabilities of C used in the .NET framework. One of the failings of C is it's very easy to make mistakes. You can, for example, have memory that you used and then you're not using, but another program could access. Or you could make a mistake and have two variables accidentally collide. And so many computer security failings that have led to all sorts of viruses and hacking come from the ways you can make mistakes in C. So this litany of Go, Rust, Flutter, Dart, Kotlin, Swift, those are all more modern languages that are designed to prevent the sort of things that can go wrong in C programming. And there's been a slow pendulum away from C towards these languages. They're fairly similar in how you program them, but they look after the sort of mistakes you can write in C. This group of languages has religious adherences. These are functional languages where you describe functions and how they relate rather than steps as a different programming paradigm. These are scripting languages. When you use a terminal, the terminal itself is programmable. And I write simple scripts in them for things that have to do with utilities, automating things you type in the terminal. APL is far and away my favorite language, and it's completely unintelligible. It was designed as a way to write math, not program, but is a beautiful programming language. It's not used anymore, but it lives on in part in Python. So Python is a beautiful language, designed from the ground up. It pulls together the best features of APL and also Lisp. And it's, unless you really know the history, it's not clear they're there, but they're actually lurking in Python. It's a very high level language. So Python, I'm going to talk a lot about performance. Python is interpreted, which makes it slow, but there's a number of ways to speed it up. So it's very well documented. There's a good Python has its own tutorial. Within Python, there are many different packages. There's been a lot of fragmentation. This is a famous cartoon about the fragmentation of Python environments. I use a tool called Conda that helps you manage the environments in Python. And then PyCharm is an editor closely connected to Python. There are many editors you can use, but PyCharm is a Python flavored editor. So I strongly recommend Python as a beautiful and very powerful language. And so for things like graphics and machine learning, it's become the staple, and I'll show you lots of those examples. Processing is a desktop environment. And the way to understand processing is Arduino came from processing. So if you like being in the Arduino environment, you'll like processing. You can think of processing as Arduino on the desktop, or you can think of Arduino as processing that's embedded. And then P5.js is a JavaScript version. So it's the spirit of processing, but native for the web. Java, I wouldn't recommend for anything new. It's designed as a language that you could run anywhere, has a complex history. JavaScript has nothing to do with Java other than having similar letters in the name. It was a scripting language for the web. So Ricardo, I'm going to talk about priorities in a second. JavaScript started as scripting on the web. It is not a beautiful language. It had a lot of limitations. It's been standardized and extended in ways that deal with it. It's very well documented. Mozilla runs a platform that's a great reference for JavaScript documentation. And then a ton of effort has gone into JavaScript because of the commercial impact. So Node lets you run JavaScript out of a browser. V8 is the JavaScript engine, and it does just-in-time compilation. So even though it's interpreted, it gets compiled on the fly. That makes it faster. And I'll show you speed examples of it. And then these are some performance extensions. LabVIEW, Simulink, all of these are visual data flow. These, instead of writing lines of code, you make pictures and diagrams for your programs. These are modular scripting environments in JavaScript descended. So mods that you've been using to control machines is a general programming environment. In the machine learning era, Copilot is a tool with GitHub that lets you use AI tools to help you program. And ChatGPT can write surprisingly good code. They come with strong disclaimers. These AI programming environments can infringe copyrights. And further, they can write code that's almost right, but not quite, but is subtly wrong, but they're growing in importance. And so there's been a growth in what are called low code and no code environments, where instead of writing lines of code, you describe what you want to do and the environment fills in how to do it. And these are growing in importance. So against that background, I would strongly recommend learning both Python and JavaScript. There's a lot, and we'll see examples, there's a lot of applications today that are best supported in Python. And there's a ton of web development that happens in JavaScript. So it's worth learning both of those. And I would experiment with the AI tools, but experiment with caution. They're powerful, but also dangerous and quickly unfolding. And they augment you. They're not a substitute for learning how to program. So pick a language. And again, I would start by learning Python and JavaScript. Then you need to talk to the devices. And so for serial communication, which we've been doing, Python has a binding PySerial. Node has a binding for JavaScript serial port. And a really interesting thing is web serial. So Google descended browsers support this. So Chrome, Chromium, and Edge. It lets you talk to a serial device right from a web browser. I don't know if they have a table at the end. So Firefox and Apple hate this and will never support it for security. So you can use this to write JavaScript to serial devices. But you're limited to those browsers. Gideon is asking about a language in a week. So the answer is yes, and it comes back to Hello Worlds. You can't master a language in a week, but I'm going to give you lots of examples in each language. In a week, you can learn to start from an example and modify it. And over time, you'll learn to write from scratch. But for this week, I'll show you lots of examples, and you'll see lots of examples from other people to get you started. I2C, we've seen these are Python and JavaScript bindings to talk to them. USB we're using, these are bindings. ERDA for infrared. Visa you probably won't see, that's for talking to instruments. Let's see, Hank is putting in a vote for Perl. this next list of all of these acronyms, and of these, I would start with MQTT. What these do is, so far I've talked about getting a message between two devices, but let's say you have a farm and you have a number of agricultural sensors. You have plumbing for irrigation, you have tractors out on the farm. To do that, you need to measure a number of different devices, and some devices generate information, some consume information. You have to pass messages between them. You have to figure out who's authorized to talk to whom. And so MQTT is a broker. It's a framework to manage communication across many devices. And these are a number of other different ways to do that task. And then finally, last week I introduced sockets that speak to the internet protocols. Web sockets are a simpler version for the web. And so in this example, I've got a web page and I'm talking to an embedded device, but rather than using web serial, I'm using a web socket to go from the web browser to a server, which can be on the same computer or a different computer. And then the server has a hardware serial interface to the device. And so that's getting data into a web page. So pick a language, pick an interface to talk to the device. Then you're going to get data back from the device. And so then come how you manage the data. So JSON and TOML are ways to package it. And the FabLab inventory, for example, is using TOML. So if you go to, let's go to a week, embedded programming. Here's an inventory for embedded programming week. But if we go into the inventory project underneath it, in here is TOML. So here's a human readable file, and this makes a data structure that then gets turned into the web pages and all the different ways you can view them. So that's a simple data structure. You can use spreadsheets. There's a limit to the complexity. Pandas is a Python database interface. These are open source databases. But there's a somewhat common misconception, which is you really only need databases if the data set is bigger than your memory. If you can fit the data in memory, you don't really need databases. You can just look into data structures in memory. So these really come in when you're managing much larger amounts of data. Okay, next comes the user interface. So this is where you put up things like buttons and sliders. And so if we go to mods and open a workflow. So in this workflow, I can open a dialog to pick a file. I've got fields where I can enter things. I've got options where I can choose, click among these different options. And all of those are elements for user interfaces. So first, you can build complete user interfaces in a text terminal with curses. Curses is a surprisingly environment. I've shown this occasionally, where you can build complete like 3D video games just putting characters on a screen. So that's interesting because all you need is a text terminal to see it. Very simple rendering. TK is a set of interfaces, and Tkinter is the Python bindings. So if we take in the input device week, if we take, say, temperature, here I've got a bar graph showing temperature. And so that's a Python program. And so in this Python program, yeah, the video game I just said was ncurses. You can build complete video games. I'm going to show you more powerful ways to do video games, but you can make a simple text video game in curses. So to do the bar graph I showed you, this is Python. And here I'm importing serial to talk to hardware, and I'm importing Tkinter to talk to the user interface. And then I open the serial port. This is where I create a window. The window gets a title. A canvas is something I can draw on. I'm creating text and some graphics. I'm putting it on the screen. And then here I'm telling Python to call this periodically. And so once it gets called, in the idle routine, it reads in data from the serial port, it calculates the temperature, then down here, it updates the text, it updates the rectangles, it draws it, and then it says, call it when you can next. And so that all of that puts up some text and a bar graph. That's in Python using TK. Just about any Python will support that. And it looks the same everywhere. Wix does the same functions, but what's different is TK always looks like TK. Wix aims to look native. And so on a Mac, it looks like a Mac. On a PC, it looks like a PC. Otherwise, it's similar. All of these do the same things. They have buttons, sliders, dialog boxes. They have interesting histories. People like each of them. But in the end, not strongly different. Then forms are an early part of web standards, still standard supported. This is where you put in forms that you can fill in. If we come back here, in mods, this is JavaScript. And if we open this, all the elements you see on the screen, these are from the forms part of the web, the graphics, all of these elements. In mods, you can open a module and you can see its own code. And so if you look at the code, all of this is using HTML forms to put up the user element. So nothing to install, very simple. It's always supported on the web. You can make UI elements with that. Then come endless things after that. So JavaScript had limitations that led to jQuery, but jQuery has all sorts of widget elements now beyond that. Dat GUI has nice widget elements. Bootstrap, Flat UI, all of these are widget elements for building interfaces in JavaScript. There's too many of these. These manage, once you have multiple sets of libraries and frameworks in JavaScript, they help building applications that are more than one file with their dependencies. And then this litany, all are versions of, you might be targeting a desktop. You might want it to work differently on a tablet. You then might want it to be on a phone, and it would need to work natively and differently in Android or iOS. And so these are all different versions of, you write in one framework, but you can present it across many different frameworks rather than writing different applications for each one. So these are tools to build user interfaces. Then after that comes graphics. So X and Java are historical. Here are two examples. So I'm going to show you this wiggly line, sine of X over X. That's the line, that's the image. That's doing Canvas. Canvas is a web standard, and this is like drawing with a pixel program. So if we open this and look at the code, this is JavaScript. I'm creating a canvas for drawing. I set the width and height of it. This lets me draw on the canvas, and then I clear the canvas. I start a line. I'm moving to points. I stroke the line, and it draws it. And so that does that. And then Jason is noting this is the hypnosis part of the class. Here, I'm making a 2D array, and I'm putting an image on the screen. So these have no notion of objects. It's just simply pushing pixels to the screen. This is good if you want pixel level control. This is going to look the same, but it's very different. This looks the same, but this is using SVG. SVG is a standard for 2D graphics on the web. It's a beautifully written, powerful standard. So here I create an SVG element on the screen. I draw my lines, but the crucial distinction here is I don't redraw it every time. The lines have an identity, and I can change their attributes. So I'm moving the line rather than redrawing it. So, and also Canvas is fixed resolution, SVG is resolution independent. So SVG is good is if you have shapes that have identity and you want to move them around the screen, not just redraw them from scratch each time. WebGL is 3D graphics on the web. You can talk to it directly, but that's very low level. So I won't even explain this. I'll talk a little bit later. But typically you use this at a high level. And the now standard way to do it is 3JS. 3JS builds a high level application on top of WebGL and makes it easy to do 3D graphics. So I'm going to do 3 versions. Here's our lines again. And if we look at this, in 3JS, I make a scene. I put a camera in the scene. The renderer tells it how to draw it. And then in this really simple one, I'm just putting lines in the scene. So I could do that with any of the other tools. Here I'm doing the images. And so I set up the scene. And here I put a geometry and I change the properties of the geometry. So you could do those with any tool, but it's powerful to do it in 3JS because it's talking directly to your graphics hardware. But then more interesting is I can do this. So now this is JavaScript making my wiggly line, but now I'm doing it fully in 3D. And so you see it's lighting it and shading it and rotating it. So let's look at that code. It's surprisingly simple. So again, I set up a scene. I put a camera in the scene. Then here I'm making the geometry. And there's a number of different basic geometries. Here, it's a mesh of points. Then I'm giving material properties to it. I'm adding it to the scene. I'm putting lights in the scene. And then when I animate, what I do is I update the position of the mesh. And then I have to tell the renderer what I changed for it to redraw it. And then I ask it to draw it. And once I do that, I get this. And so there's all sorts of 3D graphics you can now do just in a web page with Three.js. OpenGL is a underlying standard for how you do 3D graphics. Anymore, you don't need to talk to that directly. WebGPU is a current standard, and to do graphics, increasingly almost all hardware have graphics processors. WebGPU lets you talk to the graphics processors, both for graphics and also for computing, which I'll talk about at towards the end of class. PyGFX is a really nice environment for Python to talk to WebGPU. It's got a really fun gallery of of cool 3D graphics examples. And so here's my same wiggly lines, but now instead of doing this in a web browser, I'm doing it from Python. And it's really simple here. So I'm going to talk about NumPy shortly in Python. In Python, I bring in GFX. I start a scene. This is similar to Three.js. I'm going to put geometry in the scene. I'm going to put lights in the scene. And then to update the scene, I change the coordinates of the points, and I tell it to draw it and show the scene. And all of that lets me do 3D graphics from Python. Tai Chi is a framework for accelerating Python, which I'm going to shortly talk about. And in particular, it also includes graphics. So here's a fun version. Here, instead of making a surface, I'm moving lots of little particles around. And so in Tai Chi, I calculate all of that. I put them in the scene, and I tell it to draw it. So PyGFX and Tai Chi are easy ways to do powerful 3D graphics from Python. And then finally, for 3D graphics, Unity and Unreal have free versions of game engines. Godot is an open game engine. And early on, I had showed the physics engine in Blender. Blender is easily scripted in Python. So you can use Blender to do your graphics and have it talk to your devices. And then that can sit on top of all four of these have complete physics engines. So rather than programming, let's see if we go back to this example, rather than you programming how the chain swings, you can set it up, but the physics engine itself calculates how the chain swings. So those are options for doing graphics. Then to make sounds, SDL is a cross-platform multimedia library. Pygame is a binding to it. And nominally, it's for making games in Python, but what it gives you access to SDL. So that lets you play sounds, record sounds, play videos. Open Frameworks is a framework for multimedia, and then OF Python is bindings to that. And so those, again, let you play videos, record video, play audio. And then HTML5 is a set of extensions to the web. And in particular, it includes audio and video. So I'm going to open this, and let's see, let me get to, so when I play this, you'll hear a thump. Okay, I'll do it again. So the thump you're hearing is I'm turning this wave into a sound. Yeah, I guess it's more of a whoomp than a thump. And so what I'm doing here is in JavaScript, I access the audio device, I fill a buffer of sound, and then I ask the audio device to play the sound. So that lets me do sound from JavaScript. Let's see, there's a debate. Ronan is hearing a laser saber. Then this is an example where I'm doing video on the web. So I'm getting video into JavaScript and I'm doing image processing. And so if we look at that, I get the video device, and then I've got a number of routines in the JavaScript getting the video in. So those let web pages talk to audio and video. Next, virtual reality is where you plug your eyes and look into 3D graphics. Augmented reality is where you overlay so you can see the outside world and the virtual world. And then MR, XR are names for the umbrella for mixing all of these. And so this is rapidly unfolding. So there's a standard being developed for doing that on the web. But in particular, what's nice is if you use 3JS and JavaScript to make 3D worlds, you can immediately plug those into VR and AR. So anything you do in 3JS with the 3VR controller, it'll produce output. And instead of doing it on a screen, you can put it in VR and make it an immersive 3D environment you can go into to be with your data. Then all of these are rapidly unfolding, but these are all AR development environments. And so what these let you do is if you feed data into them, they overlay the 3D environment with a 2D scene through the camera. And so one of the really fun things you can do with this is with these AR environments, you can take your project running and you can actually like visualize the data as 3D graphics coming out of your project. So you can overlay the virtual and physical. And so these are a number of different evolving environments for doing AR in, that was Google versions. This is the 3JS AR version. And so there's been really interesting work on building, let's see, Jason is noting about Google Glass. Glasses to do this have had a mixed history, but what's beginning to get traction is just doing it on your phone. So you can use one of these tools to send data into your phone and have your phone look at a project and let you see virtual things coming out of the physical object. So that's VR. Then comes math. So typically, once you're bringing data in, you want to do math. You want to analyze data, process the data, graph the data. And so this link is into, this is a text I wrote for a mathematical modeling class. And I'm right in the middle of updating it. These links, many of them are rough chapters. I'm teaching it right now, so I'm adding these final chapters. That talks a lot about the mathematical methods. These are underlying libraries. You likely won't see them. MATLAB is a commercial math tool. I strongly recommend NumPy and SciPy. So what NumPy does is it extends Python for math. And so it adds a number of powerful operations to Python that I'm going to show you. Then matplotlib is powerful graphing for Python. And those are both freely available, open source, cross-platform. And so NumPy plus matplotlib plus Python is a powerful package. So let's look first. Here's an example where I've graphed my function and I'm zooming in on it, and then I'm going to save it and export it in a few different formats. And so all of that I just showed you is shockingly simple. This is the whole program. So it's Python. I'm going to bring in NumPy, and I'm going to bring in matplotlib. This, instead of a number, this makes x all of the numbers between -15 and 15 in steps of 0.2. So x is a vector. It's a list of numbers. This line, it's just one line, but this says take all the points in x, take the sign and divide by x. And this one line says take x and y, those lists, and plot them, and then show me the plot. And that's all you need to do to make the graph. Then you can animate it. So you can have a graph, but you can animate the graph. And so if we look at that, this says instead of one plot, I want to make it interactive. And so now I draw my data and I tell it to put it on the screen. And so now I can plot my data interactively. I can do that with my, as Jason described it, hypnosis pattern. And again, with the beauty of NumPy, it's really simple. This is a list of numbers. This is a list of numbers. This turns it into a 2D grid of numbers. This calculates all the points in the 2D grid, and then this pushes it to the screen. And then I can do the whole same thing in 3D. So now this is a 3D plot. And to do that, all I have to do is, it's this tiny program. I make my surface and I tell it to draw the surface. So matplotlib, with Python, you can read in your data and then you can make beautiful graphs of your data. Then these are notebooks. So what these let you do is, so far I've just been showing you Python programs, but now here, this is a notebook where I've, these commands make that one, these make that one, this makes that one, and I can run the whole thing interactively. You can run these notebooks locally, and Colab is a Google service that lets you run the notebooks in the cloud. You can, so it's sort of like Google Docs, but for math. Then Plotly is another plotting package. You can use it from Python, but in particular, it has a JavaScript binding. So here now I'm doing sine x over x, but instead of just lines, it's a graph. But now I'm doing it in a web browser. So if we look at this, it's pretty simple. I bring in Plotly. I ask Plotly to make a plot, and then I update calculating my points and telling Plotly to draw it. And that's all I need to make, rather than just wiggly lines, to make a graph in a browser. Let's see, Jason is noting Google's Bard coding to Colab, rapidly unfolding as Google responds to ChatGPT. So Plotly lets you make graphs in a web browser. Then most of the examples you saw from Nadia come from D3. So far, I've shown you graphs that look like graphs. D3 is really beautiful in, this is a gallery of all these beautiful ways to represent data. Let's see, Georg is adding this link. And so if you browse these in D3, it's not just simply a conventional graph. There are all sorts of ways to visualize data, ways to present data. And you see these when you browse like a news site visualizing election returns, for example. All these sorts of interesting ways to visualize, you don't have to do from scratch. These are all built into D3. So once you can get your data into a browser with JavaScript, with D3, you can do all of those. And Nadia's page is full of examples for that. So now we come to machine learning. In the embedded programming class, at the end, I talked about these things. This is, I'm going to talk about TensorFlow as a framework. This is TensorFlow and microcontrollers. This is TinyML. This is Expressif's learning, Edge Impulse. Those are all ways to do AI embedded. So then for AI on application desktops, so this is when you talk to ChatGPT, what you're talking to. The two most common frameworks are TensorFlow and PyTorch. TensorFlow is more mature. It's widely used. It overlaps with TensorFlow JS, which lets you run TensorFlow in the browser in JavaScript. So that lets you do machine learning in the browser. Let's see. Jason, I don't have any. Yeah, Jason is asking about. There are a number of embedded platforms for AI. They're evolving very quickly. At this point, I'm more interested in just the general purpose embedded processors. One step up from that are the compute accelerators. But there's sort of a gap in between. The compute accelerators are maturing on application programming. They're still evolving very quickly for embedded applications. I don't have a preference for that yet. And that's rapidly evolving. So TensorFlow is more mature. PyTorch, on the other hand, is more recent and is much more heavily used in research. And I'd say much more current machine learning work is done in PyTorch. So PyTorch extends Python for machine learning. And I'm going to just do a little example. We could do easily the whole scope of Fab Academy just on machine learning. And we may in the future add an Academy class on embedded AI. But I'm just going to walk through a simple example. So this is a PyTorch program. And what it does is, it's a famous historical example. It just learns the XOR function. So XOR is a simple logic function that the truth table is 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0. So it's just a simple logic function. And these are the steps, and this shows you what it is that PyTorch and TensorFlow does. So I'm in Python. I'm going to bring in PyTorch. here, this is similar to NumPy. If you take, this is X, these are my inputs, Y are the outputs, and this is the mapping between them. And all I'm going to do is I want to make a function that learns that relationship between inputs and outputs. So this is 0, 0, 0, 1, 1, 0, 1, 1. Those are my inputs. And then I'm telling it what type of data, a floating point number. Then these are my outputs, 0, 1, 1, 0. And then this is, for the way it's organized, these can have a shape, and this makes it orient vertically. Then in machine learning, the simplest machine learning that'll take you very far is you have nodes, you connect them in a network. There's connections between them that have weights. Then each of the outputs goes through a function, and then you have some number of layers until you get to the output. So in what I'm doing here, this is the simplest sort of architecture. I'm just making a sequential model in layers. There are more complex types of models. So this says make a linear layer that takes 2 inputs and outputs. Then these activation functions, what they do is Canch looks like this. And it squashes the output. So near the origin, it's linear, then it curves nonlinear, and then it saturates. And there's a lot to say about why you need them, but that's an example of what's called an activation function. So here I've got a linear layer, I've got an activation function, and then I've got another linear layer, and this ends at a single output because I'm only predicting one variable. Then in this diagram, each of these links has a weight. There's a weight for each link, which says how strong the connection is. I've got to initialize those. And so here I'm initializing them with random values. Then I'm going to train my model. So the loss function is how you measure how well you're doing. And MSE is mean square error. That says take the error. I'm going to make a prediction. I'm going to compare it to the true value. I'll take the square of that and I add all of those up. So that's how I'm going to measure my progress. And then the optimizer is the strategy to train it. So I've got in my network, I'm going to put in input data. I'm going to predict output data, and I'm going to compare it to the real value. And then that gives me an error. And then I use the error to adjust the weights. And that's how I train the model. So here I have to tell it the strategy for doing that. And I'm using Atom, which is a common training strategy. And now I'm going to do the training. So I take my data, I predict the output, I then calculate the error. This clears the gradient, and this is the profound step, which is you can think about, I've got a space of, this is the space of all of the weights, which has lots of dimensions. And then this is my error. And you can think about this as a surface. And what the training does is it goes downhill to find a minimum of the error in the space of all of the training. So what this does is this one line, error.backward, is the magic of what TensorFlow and PyTorch does. What this says is take the error and then find the gradient of my model, and then use my optimizer to take a step to improve it. And I print my progress, and then I'm done. I print the output. And so if we come back to here, this first column is the training epoch, how many times I've made a step. This is the error between my prediction and reality. And it starts bad, but it gets good. And this is a very easy problem. And then here, this is the predictions at the end, and it should be 0, 1, 1, 0. And you see, it did a good job of learning the model. So this is a toy problem, but it shows you all the elements of defining a machine learning model, setting it up for training, running the training loop, and then using it. There, I'm predicting a function, but I could do the same sort of thing to categorize it. Instead of predicting a function, I could output categories, and the input instead could be sound versus time. It could be images, but they all share the basic ingredients of the simple example. So that's what TensorFlow and PyTorch do. We could spend the whole cycle of this class just on unpacking machine learning. I haven't yet updated it, but I'm going to be adding an updated chapter on machine learning for this class for updating this text. You'll find tons of material online, but those are the basic elements of using one of these machine learning environments. Okay, so that's math. Now I'm going to talk about performance. So for many years, I've done the following simple operation. What I'm doing here is I'm taking pi and I'm writing it as this sum. And the sum has an interesting property. Each term in the sum you can calculate separately. So you can send that out to many different processors. And then you need to gather the results and add them all up. So it's called a scatter-gather calculation. And we care about performance because many things you're going to do are going to be limited by the speed of the computing. So as you start doing machine learning or synthesizing sound or controlling systems, you're going to be limited by how fast it runs. And that's both on the embedded systems, on the desktop systems. And so I'm going to cover a number of ways to measure and then speed up your programs. Now, in this table, this is gigaflops. That's 1 billion floating point operations per second. So if we look at this table, this is 0.0000001. That was the original Intel processor, the 8088. I've been doing this calculation for a long time. And then that's the slowest one. And then here's the fastest one. And this is on Summit, which was until recently the world's biggest computer. And so let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's 13 orders of magnitude from the slowest to the fastest calculation. And so now I'm going to walk you through all these different ways to speed stuff up. So let's start with, this is the calculation in Python. So I write a Python program and I do that calculation. And if we do the Python, on a desktop, I get 0.03, which is slow. Then this is, let's see, the if you look at this version, let's see, yeah, let me stay, all of these are a desktop processor. This version is 10 times faster in Python. So what's that doing? This is using, remember NumPy, the environment I told you for math in Python? This line creates a list of values from 1 to n. And then this one line, I here is a list of values. This one line calculates my sum for all of them and gives me the result. So writing loops in Python is slow. That avoids the loop. And so that gives me the answer. Remember, before we were at 0.03, now we're at 0.4. So that's good, that's faster. Here's a C program. So that does it in C. And right now, that's about the same speed as the Python with NumPy. So then this version is JavaScript. Now, if you look at the JavaScript version, the C and Python were 0.4. The JavaScript here is 10 times faster. That's because JavaScript does just-in-time compilation. So when you run the JavaScript, because it's so important commercially, just in time it's compiled, and that makes it run faster. Okay, so that's good. We're now starting to speed up. Now, here's another Python version. And this Python version is 10 times faster. This is using something called numba. So what numba does is Python is interpreted, but numba lets you take your Python function and you put what's called a decorator. And this says to numba, even though this is Python, I want you to compile it and make it go fast. So numba lets you compile Python, and so we're now 10 times faster. So that's good. Now, remember, the C was disappointingly slow, but that's because I just compiled it. C can do many optimizations. So here's that same C program, but now I'm 10 times faster still. And here what I'm doing is I'm telling this C compiler to optimize it, to make it go fast. Then here's my JavaScript again, but now I'm up to 16 gigaflops, 10 times faster. And what I'm doing here is I'm using workers. So if we look at the code, well, actually, let me first run this one. So I'm going to run this with one worker, and I get 2 gigaflops. 4 gigaflops. I'm going to run it with 2 workers. I get 6. And now it stopped. I'm up to 12. But now it's slowing down. That's because I have 4 cores on this computer. So what this is doing is what are called web workers. A processor on a desktop computer increasingly has multiple subprocessors. Workers let a JavaScript program talk to multiple workers. And that's very powerful because you can have one doing the serial communication, you can have one doing math, one doing the user interfacing, and they don't slow each other down. So that's doing parallel programming in JavaScript. In this version, I'm using Python, but I'm now using another Python program, and that one lets me talk to multiple processors to speed up the Python. Then from here now, I'm going to leap ahead to, do you remember I told you about Tai Chi? So you might have gotten lost. Remember, this column is gigaflops, and the original Python program was 0.03. This is now 1,000. This is a teraflop in Python. So what I'm doing is Tai Chi lets you talk to graphical processing units, GPUs, to speed up your math. Normally, to talk to a GPU, you have to write really tricky code. This is called CUDA code, and it's hard to learn how to write that. But it's really easy in Tai Chi. So this is a Python program. And in my Python program, I'm telling it, I want it to run it on a, this says I want to run it on a GPU. And then this little routine calculates pi. But Tai Chi is so smart that when I tell Tai Chi to run this, it actually takes it from the CPU and packages it and tells the GPU to run it and gets the results back and lets me run at a teraflop using a graphical processor. And then finally, the crazy numbers up here are using what are called MPI. And MPI lets you, oh yeah, sorry, Stephen is noting the V100 is a big GPU. So to use that, I don't keep one in front of me. I use that in the cloud. So if we go to AWS EC2, and if we look at a P3 2x large, using one of these big GPUs is $3 an hour to rent it from Amazon. Then, yeah, and there's a lot to say what's going under the hood. The GPU has thousands of processors, and what Tai Chi is doing sitting on top of CUDA is coordinating them. And then finally, these numbers, this is up to petaflops. And to do petaflops, for the sort of work I do at MIT, sometimes we need to use the world's biggest computer. So this is Summit. And so this calculation, remember the GPU has 5,000 cores, and this calculation used 12,000 GPUs. And it's using what's called MPI to coordinate that. So stepping back from all of that, that's a tour through lots of different ways, from compiling to packaging to multi-core programming to speed up your application. And almost anything you do at some point is likely to need to run into those performance limits. Then finally, deploying, once you build your application, you might want to post it so somebody else can get access to it. So AWS, yeah, so Jason, the processors in GPUs are incredibly specialized. They're far from general purpose. They're streaming multiprocessor units. They need to do very limited tasks. They're very different from the general purpose embedded processors. Amazon runs AWS. EC2 is a service where you rent computing hours, and it ranges down very cheaply. So the simplest servers are 10 cents an hour. You can get a well-equipped one for 50 cents an hour, and then on up for more powerful ones. EC2 lets you make custom ones where you pick the processor and memory and everything. Lightsail are prepackaged ones. Lambda is a neat thing. Instead of renting a server, you just send an application to the cloud. Parallel cluster lets you make groups of more than one server if you need them. And then this is a link to remote desktop commands. And what these let you do is build a graphical user interface to them. So in class, when I've shown you a web browser and I run applications, I'm running them using a remote desktop in the server. Google has its cloud, Microsoft has its cloud. Those are easy to use to run servers in the cloud. This is slightly different. What this lets you do is instead of running a server, you just support an application. So they configure the server and it serves your application. And then these are tools that let you package your application to deploy to the cloud. So all of these let you take your homework from this week, but turn it into a service that you or other people could access. And then just a note, all code gets attacked all of the time. The servers, this server you're seeing that I run for the class, the server you're using for FabCloud, if you look at their logs, they're continually and consistently being attacked by people trying to break into them. So you need to look ahead to anything you to deploy. Attack surfaces are ways people can get in. It used to be security came from trying to keep things secret. At this point, it's become clear that it's much better to explain how your code runs transparently and identify where the secrecy is. And so in particular, I covered lots and lots of packages. All of these are getting patched all the time. If you deploy any of these, you need to be aware of the dependencies under them and keep them current. And so there are a number of historical famous failures in important packages that brought down big parts of the internet that depended on them. And then most of these have tools to support encryption. So even if somebody gets at your data, they can't use it. Or just some general principles for managing security. Let's see, Ricardo is noting about Arduino Cloud. That's interesting. That's new. I'm not familiar with this. Interesting. So I'll link this. This looks like its version of many of the other things I described of going from the cloud to your embedded devices. Nice. I'll add a link for that. So so again, now if we go back and look at Nadia, now you can see what she did this week was she took one of almost every framework I covered, and then she built sensor interfaces to it. So for this week, you can take data in and visualize it. You could analyze it. You could build interfaces to control. And then I covered so many different options. Just as a group, I want you to explore and compare them. So definitely start by learning Python and JavaScript. And you won't learn it from scratch. Both have good tutorials. Let's see, Hank is adding a link to a book from Nadia. Oh, nice. Let's see, I'm going through a couple notes in the chat.
If you go down, you see examples and also how she made it and so on.
Oh, nice. Yeah, she has just a gorgeous data design sense. And this week can be really expressive. Oh, yeah. Yeah, she, if you can go from 1 to 10, she always does 11. Yeah. Good. So start by, so Python and JavaScript have good tutorials, and I gave you lots of starting examples today. You can find lots of examples. Write an interface or to an input or an output. Think ahead to your final project. This can run, from anything from a embedded on a Raspberry Pi to a phone to a tablet to a desktop. And as a class, just explore as many of these options as you can and build interface applications. So with that, no recitation this week, and then we'll be back next week for wildcard. And as always, Saturday open time. So happy programming. This is a very expressive week. I look forward to seeing both what you do and what tools you use. Bye.
Bye.
Bye
Chao.
bye.
Hasta luego.
Nos
Bye.
vemos. Chao.
Adiós.
Adiós.
Au revoir.
Bye.